LGBTQ. Claude Code, Codex, Chat, Explorer, Topic Music Generation. Abstract the present work is about the synthesis of piano sound based on the grounds of physical principles. For that, first the acoustical properties of the piano have to be understood, since the underlying physical phenomena establish the framework for the model-based sound synthesis. Therefore, the different parts of the piano were measured, and analyzed. The groundwork of the piano model lies in the digital waveguide modeling of the string behavior. Accordingly, the digital waveguide string model is thoroughly discussed and analyzed. The mathematical equivalence of the digital waveguide and the resonator bank is also presented. The partition of the piano model follows the principles of the sound production mechanism of the real piano. The hammer is modeled by nonlinear interaction. The discontinuity problem arising when connecting the hammer to the string is investigated, and new solutions for its avoidance are proposed. The instability problems of the hammer model are overcome by a novel multi-rate implementation. The possible use of a nonlinear damper model is also discussed. The string simulation is based on the digital waveguide. For beating and I-stage decay, a new parallel resonator bank structure is proposed. The soundboard model consists of a feedback delay network with shaping filters. A new technique is presented to reproduce the attack noise of the piano sound in an efficient and physically meaningful way. Concerning the implementation issues, a multi-rate piano model is proposed, which resolves the problem of different computational loads presented by the string models of the low and high register. Additionally, the calibration of the piano model is described. A new loss filter design algorithm is presented for the calibration of the digital waveguide. The new technique minimizes the error of the resulting decay times and also ensures the stability of the feedback loop. For the one-pole filter as a special case, a novel filter design technique is proposed. It is founded on the new theoretical results of the appendix concerning the decay times of a feedback loop containing the one-pole loop filter. A robust technique for the measurement of beating and I-stage decay is presented. This is used for the calibration of the parallel resonator bank. The methods and techniques proposed here are described with the application to piano sound synthesis. Nevertheless, most of them can be exploited for the efficient synthesis of other musical instruments as well. What's the big idea? Someone wanted to make a computer-generate piano sounds that actually sound like a real piano. not by recording samples, but by writing equations that simulate how a piano physically works. Think of it like building a virtual piano from scratch in code. Why measure the real piano first? Before you can fake something, you need to understand it. So they took measurements of a real piano's parts, strings, hammer, soundboard to know what the physics actually looks like. What's a digital waveguide? It's the core trick. A piano string vibrates by sending waves back and forth. A digital waveguide is a clever mathematical shortcut that simulates this wave bouncing without having to compute every atom in the string. It's efficient and grounded in real physics, the model's moving parts. Hammer, when you press a key, a felt hammer hits the string. Felt squishes in a complex, nonlinear way, which makes the math unstable unless you're careful. They fixed that. Strings simulated with the waveguide. Real piano notes have beating a wavering wobble from two close frequencies. An I stage decay decays fast at first, then slowly fades. They built a special structure to reproduce both. Soundboard, the wooden board that gives the piano its body and resonance. Modeled with a feedback delay network, a loop of delayed signals shaped by filters. Attack noise, that thwack when the hammer strikes. Often ignored, they modeled it properly multi-rate. Why it matters: low notes and high notes need wildly different amounts of computation. Their multi-rate approach runs the low note math slower and the high note math faster, saving CPU without sacrificing quality. Calibration. A model built from theory won't sound right without tuning it to match a specific real piano. They developed new algorithms to measure a real piano's decay behavior and fit the model's parameters to it, like adjusting dials until the simulation matches the recording. One-sentence summary. Build a physics-based piano in software by modeling the hammer, string, and soundboard separately. Calibrate each part against measurements of a real piano. And you get a synthesizer that sounds like a piano because it behaves like one. Abstract. The present work is about the synthesis of piano sound based on the grounds of physical principles. For that, first the acoustical properties of the piano have to be understood, since the underlying physical phenomena establish the framework for the model-based sound synthesis. Therefore, the different parts of the piano were measured and analyzed. The groundwork of the piano model lies in the digital waveguide modeling of the string behavior. Accordingly, the digital waveguide string model is thoroughly discussed and analyzed. The mathematical equivalence of the digital waveguide and the resonator bank is also presented. The partition of the piano model follows the principles of the sound production mechanism of the real piano. The hammer is modeled by nonlinear interaction. The discontinuity problem arising when connecting the hammer to the string is investigated and new solutions for its avoidance are proposed. The instability problems of the hammer model are overcome by a novel multi-rate implementation. The possible use of a nonlinear damper model is also discussed. The string simulation is based on the digital waveguide. For beating an I-stage decay, a new parallel resonator bank structure is proposed. The soundboard model consists of a feedback delay network with shaping filters. A new technique is presented to reproduce the attack noise of the piano sound in an efficient and physically meaningful way. Concerning the implementation issues, a multi-rate piano model is proposed, which resolves the problem of different computational loads presented by the string models of the low and high register. Additionally, the calibration of the piano model is described. A new loss filter design algorithm is presented for the calibration of the digital waveguide. The new technique minimizes the error of the resulting decay times and also ensures the stability of the feedback loop. For the one-pole filter as a special case, a novel filter design technique is proposed. It is founded on the new theoretical results of the appendix concerning the decay times of a feedback loop containing the one-pole loop filter. A robust technique for the measurement of beating and I-stage decay is presented. This is used for the calibration of the parallel resonator bank. The methods and techniques proposed here are described with the application to piano sound synthesis. Nevertheless, most of them can be exploited for the efficient synthesis of other musical instruments as well. Keywords: digital signal processing, digital waveguide, musical Bank 2000 is directly load-bearing for what we're building right now. 3 concrete connections. 1. The loop filter we already implemented came from it. The one pole at our LP state equals 1A Cur plus a LP state that replaced the broken averaging filter in EXP007. That's the Bank 2000 design, published formally in Bank and Valimaki 2003. Our synthesizer uses it right now in production point 2. The next item on the critical path is also Bank 2000. Open item number 1 in the README is attack noise. Inject a filtered noise burst at node on 1 pole LPF cutoff proportional to F0, scaled by velocity. That prescription comes directly from Bank 2000 section 5.4.4. It's the primary thing standing between us and CNN 14P, piano 0.50.3. The gap analysis maps exactly to Bank 2000's chapter structure. The architecture diagram in the root cause report, green circle, orange circle, red circle blocks, is essentially comparing our synthesizer against the Bank 2000 complete model. The things we're missing, a real soundboard model, FDN, proper eye stage decay calibration, hammer felt nonlinearity, are all chapters in that thesis. Open items 3 and 6 in the README trace directly back to its short version. Bank 2000 is the reference design we're trying to catch up to. We've implemented the most critical piece, loop filter. The thesis is the roadmap for everything that comes next. Are you just doing the same thing Bank did, but doing it badly? Partly yes, and that's partly yes, and partly yes, and that's on purpose. Partly yes, partly yeah. Are you just doing the same thing Bank did, but doing it badly? Partly yes, and that's on purpose. Bank's entire goal was the piano itself. He spent a year asking, can I make a computer simulate the physics of a piano so accurately that it sounds like the real thing? The piano was his destination. He built the hammer, the strings, the soundboard, all of it, and then carefully calibrated every part against measurements of a real Steinway. The thesis is done when the piano sounds like a piano. Our goal is different. We are building an AI system that composes and performs music. The piano synthesizer is just one piece of that, like an engine inside a car. We don't need the best piano engine ever made. We need one that's good enough to drive the rest of the system forward, so we started with the simplest piano engine we could find. A 1983 algorithm that takes about 10 lines of code, and asked, is this good enough? We ran experiments to find out. The answer kept coming back, not yet, and here's exactly why. Each time it failed, We looked up what the piano synthesis community had already figured out, usually bank, and we adopted the specific fix we needed. Nothing more, the difference is direction. Bank started from physics and worked towards sound. We started from a simple sound generator and are working backward toward the physics, but only as far as we need to go to unlock the next stage of the larger project, so we're not doing it badly. We're doing it deliberately minimally in a larger context. Bank wasn't working in at all. Great question, and the honest answer has two parts. First, we are using Bank's work, the loop filter we implemented last week. We got the formula directly from his thesis and his 2003 paper. The attack noise we're about to add, straight from his chapter on it. We're not reinventing what he did, we're reading his work and implementing the specific pieces we need. He's our primary reference, not our competitor's second. Using what Bank did isn't a thing you can do. His thesis is a research document, not software you can download and run. It describes how to build a piano synthesizer. Someone still has to write the code. We wrote ours, we're patching it using his prescriptions now. There are ready-made piano synthesizers you can just use. Pianodeck is the best physics-based one commercially available. So why not just use that? Because the piano is not our destination. We need a piano engine that we can control programmatically, modify, understand end to end, and integrate into a larger AI composition system. A commercial black box doesn't give us that. And more importantly, if we just dropped Pianodeck into the pipeline, we'd have built nothing. The research contribution we're working toward is the whole system. The AI that decides what to play, how to play it, and a synthesis layer we understand deeply enough to verify that the output is physically meaningful. Bank built the engine. We're building the car. We just need the engine to work well enough to drive. And on that farm, he had a KS string AIAIO with a pluck here and a loop filter there. Honestly, The part we're working on right now has nothing to do with AI. We're doing signal processing and acoustic physics. Delay lines, loop filters, decay curves. This is 1980s mathematics running on a CPU. Banks' thesis is from the year 2000 and doesn't mention machine learning once. Nothing we've built in the last 2 weeks is AI in any meaningful sense of the word, where AI enters the picture is at a higher level, the part that decides what to play, which notes, in what order, with what feel. That's the composition layer the piano engine is being built to feed into. And even then, AI is just shorthand for a system trained on data that can make musically sensible decisions, which is a real thing. But it's a different layer from what we're doing now, so the grasshopper's instinct is good. If someone said, we're using AI to synthesize piano sounds, that would be misleading. What we're doing is building a physically accurate piano engine using techniques from acoustic engineering so that a music generation system, which does involve machine learning, has a decent instrument to play. The AI label applies to the car, not the engine. Right now, we're in the garage working on the engine. There's no AI in here, just physics and code. No, and the difference is worth being precise about. The YouTube kid takes an API, calls it in a loop, adds a front end, and calls it an AI music generator. There's no understanding of what's happening inside, no way to verify the output is any good. And nothing new has been created or learned. What we're doing that's different. The physics layer is entirely ours. We wrote a piano synthesizer from scratch, diagnosed exactly why it was wrong using mathematics and acoustic measurements, and fixed it using 25-year-old engineering literature that most people have never heard of. That's not wrapping an API. That's understanding a physical system deeply enough to build it. We're running real experiments. Falsifiable hypotheses, pre-registered before we touch the code, confirmed or falsified against measured data. We've falsified more hypotheses than we've confirmed. That's what honest research looks like. YouTube doesn't do that because it's slow and often disappointing. We built an evaluation framework that caught us lying to ourselves. Our synthesizer passed several tests we designed. Then we designed harder tests and it failed badly. Most people would have stopped at the passing tests and shipped it. We kept going. Now, is the composition layer at risk of becoming the LLM slapped on top thing you're describing? Yes, absolutely, if we're not careful. That's a real danger. The physics work is solid. The question of whether the AI decides what to play part will be genuinely novel or just another wrapper around someone else's model is still open right now. We're in the part that's definitely not garbage. The harder question comes later. That gut wrench is telling you something true. AI system for music generation is a marketing sentence. It tells you nothing about what's actually being built or why it's hard. Worse, it puts the work in the same bucket as every toy project that deserves to be forgotten. What you're actually doing is closer to rigorous empirical research into physics-based piano synthesis with a pre-registered experimental methodology. The experiments, the falsifications, the acoustic measurements, the gap analysis against 25-year-old literature, that's the work. That's what makes it real research, rather than a demo. The machine learning tools we're using, S01.E008, are evaluation instruments, the same way a microphone and a spectrometer are instruments. You don't call an acoustics paper an AI project because the researcher used a digital analyzer where it gets honest. At some point, the composition layer will involve learned models. But that doesn't make the whole thing an AI system. A paper about a new telescope isn't an AI paper just because the image processing pipeline downstream uses neural networks, so the grasshopper deserves a better one-liner than the one I kept reaching for. Something like, "We're building a piano that understands why it sounds the way it does." That's true, it's specific, and it doesn't make a researcher's gut wrench what label feels right to you. I was wrong, and I now understand why your gut wrenched. The composition engine is not an AI period. It is a cellular automaton, Wolfram Rule 30. A deterministic mathematical system that has been studied since the 1980s, completely unrelated to machine learning. The melody comes from bits in a CA row. The phrase structure comes from music theory rules derived from Narmer and Lerdahl and Jekendorf. The expression comes from the KTH rule system, which at RenCon 2025 beat neural approaches. None of that is AI in any meaningful sense. The machine learning tools in this project, CNN14 and MERT, are measurement instruments. They are the equivalent of a spectrometer or a microphone. You use them to ask, "Does this sound like a piano?" They do not generate anything. When a scientist uses a digital analyzer to measure a signal, we don't call their work an AI project, so what is this actually? It is algorithmic composition with physics-based synthesis, evaluated using acoustic classifiers. The piano synthesizer simulates physical string mechanics. The composition engine is a deterministic mathematical automaton constrained by formal music theory. The whole thing generates audio from mathematics alone, with no samples and no neural network anywhere in the signal path. The AI label doesn't just feel wrong, it's technically inaccurate about how the system works, and it hides what's actually interesting about the project. Three things, genuinely first. The composition problem turns out to be the easy one everyone assumes making a computer compose music is the hard part. It isn't, or at least, a 1980s cellular automaton handles it well enough that the music never repeats, never runs away melodically, and has phrase structure that listeners find coherent. The hard part is making it sound like a piano. A computer can decide what to play in 10 lines of code. Making it sound like the instrument it's supposed to be requires 25 years of acoustic physics literature and a stack of falsified experiments. That inversion of expectations is interesting second. Formal music theory beats machine learning at its own game at RenCon 2025, a competition specifically for expressive musical performance. A rule-based system built from 1980s music theory research placed ahead of neural network approaches. The rules in this project come from the same tradition. The interesting claim, which is now empirically supported, is that for certain musical problems, a carefully written set of rules grounded in how listeners actually perceive music is more powerful than a model trained on data. That's counterintuitive in 2026. Third, it's legally clean. Forever, every note, every timbre, every performance comes from mathematics. No samples, no recordings, no copyrighted material anywhere in the signal path. That's not a technical curiosity. For anyone who wants to stream or publish music generated this way, it changes everything. And it only works because the physics is real enough that the output actually sounds like a piano, the through line. Rigor matters more than sophistication. Simple math, done correctly, beats complex systems done carelessly. That last line is the answer to the second question. Let me now answer both. Did Bank produce output that sounded like a piano? Yes, but his measurement method was : he played it to people and asked them what they thought. The thesis thanks Ms. Hanna Jorvalainen for the annoying listening tests. His soundboard section contains the sentence. The earlier piano model was described to be too clean in the high range by many experts of the field. This simple technique partly solved the problem and made a large improvement in the perceptual quality of the model. That's the evaluation. Experts listened, complained, he fixed it. They said it was better. No number, no threshold, no score, just ears that was perfectly reasonable in 2000. For a master's thesis, it sounds convincingly like a piano to people who know what pianos sound like is a valid conclusion. Bank wasn't wrong to do it that way. So why not use a spectrometer? A spectrometer would tell you the exact frequency content of the sound at any moment. And it would find differences between the synthesized piano and a real one immediately, because there are always differences. But that's the problem. It finds everything. A spectrometer cannot tell you which differences matter. Imagine you measure a real piano and your synthesizer and find the 7th harmonic is 3 decibels too loud. Is that audible? Does it make it sound less like a piano? Does anyone care? The spectrometer says nothing. You need a human ear to answer those questions, or something that has learned to mimic human ears at scale. That's exactly what CNN14 is. It was trained on millions of audio recordings labeled by humans to recognize what things sound like. When it hears a sound and says this is 3% likely to be a piano, it's not measuring a specific frequency. It's saying the whole pattern of how this sound behaves over time doesn't match what pianos sound like to people who labeled piano recordings. That's a much richer judgment than any single spectral measurement. MERT is similar, but finer. It was trained specifically on music. So it has a more nuanced sense of what makes audio musical. Rather than just piano shape, the spectrometer is simpler and more reliable at measuring what it measures. The problem is that what it measures isn't what you're trying to know. The honest trade-off, Banks' method, human ears, is the gold standard but doesn't scale and can't be automated. The spectrometer is precise but answers the wrong question. CNN14 and MERT are trained proxies for human perception, faster than listening tests, more meaningful than raw spectral measurements, but they can be fooled and their judgments are opaque. None of the 3 is perfect. We use all 3 in different roles. There's no contradiction. The metrics agree with the human CNN14, gives the current synthesizer a piano score of 0.03. The acceptance threshold is 0.50. The test that checks whether it sounds like a piano is marked X-fail, meaning we already know it fails, and we committed that knowledge before anyone fled a room. The fancy methods are not claiming the output is good. They are shouting in numbers that it is broken. The humans didn't tell you anything the metrics hadn't already said. They just said it faster, and with their feet where the metrics earn their keep is not in this moment, it's in the work between sessions. You can't sit a panel of humans next to a laptop and ask them to react every time you change a constant by 0.001. The metrics let you run 49 notes across 5 sources overnight, produce a table of numbers, and find out in the morning exactly which part of the frequency spectrum is wrong, and how wrong it is. That's what EXP011 did. No humans available at 3 a.m., and you still knew by breakfast that the centroid ratio was 0.943 when it should be 1.395. The humans fleeing the room is the goal statement. The metrics are the map for getting there the map currently shows. You are not there yet. CNN14 was trained on recordings of real pianos being played, full pieces, with room acoustics, reverb, multiple notes ringing together. It learned to recognize piano from that kind of signal. What we feed it for testing is a single dry note, played alone, recorded close up with no room sound at all. It's like training a dog to recognize your face in family photos, and then showing it an X-ray of your skull and asking if it recognizes you. Technically related, practically unrecognizable, so CNN14 gives a studio-quality Salamander grand piano, a reference instrument, a score of 0.13 out of 1.0 on single notes. Our broken synthesizer scores 0.01. Both are terrible. The gap is real, but both numbers are useless in absolute terms. Here's the killer result that really demonstrates the problem. Before the Bank-Volimaki fix, the synthesizer had a fundamentally broken loop filter. We know this from physics and from measurements. After the fix, every acoustic measurement confirmed it was dramatically better. But MERT, another supposedly sophisticated metric, ranked the broken version higher than the fixed one. 0.764 for the broken synthesizer versus 0.660 for Salamander. The metric got it completely backwards. So what do? You don't throw the metrics away. You understand what each one is actually measuring. CNN14 at the piece level with full polyphonic music in reverberant conditions works correctly. That's how we use it now. MERT works at the piece level too. Neither works reliably on single dry notes. The humans fleeing the room and the metrics giving low numbers are saying the same thing. The interesting lesson from EXP011 is that some of the metrics were also fleeing the room for the wrong reasons. The skeptics are right that it still sounds bad. They're wrong that the metrics weren't useful. Here's why the experiments didn't fail to make progress. They failed to reach the finish line, which is a different thing. Look at what actually happened. The synthesizer started with a loop filter that was 3 to 13 times wrong on every note simultaneously, with the error changing direction between bass and treble. No single knob could fix it. The metrics didn't just confirm it was bad, they told us specifically what was broken and why no amount of tweaking the existing controls could ever fix it. That's what sent us to the literature, which is where we found Bank, which is where we found the correct filter. We then implemented it, and the T60 ratios, the actual physics, improved 3 to 7 times across the board. That's real progress. The reason it still sounds awful is that fixing the loop filter was step 1 of about 5. The metrics told us that too. After the fix, CNN14 still gave us 0.03. But now we know exactly why. Attack noise is absent. The Feldhammer thwack at note onset, the percussive crack you hear when a key is struck, is simply not there. That is almost certainly the single biggest remaining gap. Not a vague, it sounds synthetic. A specific missing component with a specific fix already prescribed, so the situation is not weeks of tweaking with nothing to show for it. The situation is, a physics problem was diagnosed, the correct solution from the literature was implemented, the physics improved dramatically, and the metrics correctly identified that the next bottleneck is something else entirely. The humans fled because of the attack noise. The metrics agree. The next experiment is adding the attack noise. I can't fully defend it. You're right, and the metrics were slower to say it. Here's the honest account. The treble notes sounding like a thin, plucked violin string is not a coincidence. It's exactly what the Karplus-Strong algorithm was designed to produce. The original 1983 paper was about guitar and plucked strings. That is the algorithm's natural character, especially at short delay lines where the physics breaks down fastest. The metrics did flag the treble as the worst region. EXP009 showed Merck cosine dropping to 0.475 at MIDI 84, the lowest across the keyboard. The centroid analysis flagged treble issues repeatedly. So the metrics were pointing at the treble and saying something is badly wrong there, but they couldn't tell you what it sounded like. They said treble bad in numbers. Your ear said thin, plucked violin string in one phrase. That's more diagnostically useful, and it points directly at the same root because we already know. The attack noise is missing a piano note, and a plucked string are actually very similar after the first 50 milliseconds. What distinguishes them is the onset, the hammer thwack, the percussive crack I've felt hitting steel. Without that, a decaying harmonic tone at 1000 Hz is a plucked string. That's not a metaphor. Physically, it's the same signal, so the metrics weren't wrong. But your ear got to the diagnosis faster and named it more precisely. That's the correct role for human listening, not to replace the metrics, but to say things the metrics can't, like this sounds like a violin being plucked. The metrics confirm the problem is real and locate it. The ear tells you what it actually sounds like. The attack noise as item 1 on the open list. That is not a coincidence. No, we have not proved that yet. And that's an important distinction. What we have proved is narrower. The metrics correctly rank things in the right order. Salamander scores higher than our synthesizer. The fixed synthesizer scores higher than the broken one. When the physics improved measurably, the metrics moved in the right direction. That's not nothing, it means the compass is pointing the right way. What we have not proved is that following that compass all the way to the end actually gets you to something that sounds like a piano. That remains an open bet. Here's the honest version of the situation. We are navigating by instruments in fog. The instruments are calibrated. We checked that in EXP011. But we haven't arrived anywhere yet, so we can't yet say we followed the instruments and look where we ended up. The proof of the pudding is still ahead of us. The attack noise experiment is the first real test of whether the compass is useful for navigation, not just for calibration. It's a change that is both acoustically significant. Your ear identified it, Bank identified it in 2000. The metrics flagged the treble region as broken and physically well understood. If we add the attack noise and the CNN14 score jumps from 0.03 toward 0.50, and the remaining humans in the room don't flee, that's the first moment where we can say, yes, the metrics and the ears agree, and both improve together. Until then, the skeptics are entitled to their skepticism. The claim is reasonable. The proof isn't in yet. Yes, that's research. The alternative is navigating without instruments at all, which is what Bank did in 2000. He tweaked things until experts said it sounded better. That works too. But it's slower, it doesn't scale past the number of experts you can get in a room. And when something breaks, you don't know why. The instruments we have are imperfect and partially validated. But they already did one useful thing. They told us the loop filter was architecturally broken in a way that no amount of ear-guided tweaking could have fixed, because the error was mathematical and invisible to listening. You can't hear that the T60 ratio is 13 times wrong. You can only hear that it sounds bad. The metric told us why it sounds bad, which told us what to change. Whether that's enough to land the plane, we don't know yet. The mountain is real. We might crash, but the honest answer to are the instruments trustworthy is more trustworthy than nothing, less trustworthy than we'd like, and we are actively checking them as we go. EXP011 was largely an experiment about the instruments themselves, not the synthesizer. We demoted 2 metrics that turned out to be lying and kept the ones that told the truth. That's not blind faith in the instruments. That's exactly the right way to navigate in fog. If the attack noise experiment fails to move the needle, that's the moment to seriously question whether we're flying toward the mountain. We're not there yet. That hopper is making a sharp point. N deserves a straight answer. Bank was doing fine-grained calibration. His synthesizer already sounded like a piano, recognizably, convincingly. The experts were telling him things like the high notes are a little too clean, or the attack in the bass is slightly wrong. Subtle aesthetic feedback on something that was already in the right territory. We are not in that territory. The humans didn't flee Bank's demo. They fled ours. That's not a calibration gap, that's a category gap. We are not yet making something that sounds like a piano with subtle flaws. We are making something that sounds like a different instrument entirely. And the hopper is right that this changes what feedback means. Bank's experts were useful because they could hear the difference between his synthesizer and a real piano and describe it precisely. Our listeners can't give us that kind of feedback because they're not comparing us to a piano. They're comparing us to what a piano is supposed to sound like and concluding we're nowhere near it. GTFO is not actionable feedback. It's a verdict, so where does that leave us? We are earlier in the process than Bank was when he started getting expert feedback. We are still in the phase where the synthesizer needs to enter the room before anyone can tell us what's wrong with it. The attack noise fix is the thing most likely to get us into the room. Not to sound like a piano, but to sound enough like one that a human can start telling us what's wrong with it, rather than just that it's wrong. Bank's experts were calibrators. We don't have calibrators yet. We need to earn them first. Now there's the key passage. Bank wrote at the end of his thesis, "The piano model described in the thesis gives good results. Nevertheless, there is still much to do in making the model more efficient and the sonic outcome more realistic." And his footnote says good results. Then his future work list is a full page of things still missing, and crucially, his personal motivation for wanting a real-time implementation was, in his own words, the author wishes to play his own instrument. He hadn't played it yet. The thesis was about building the physics and calibration framework. The playable instrument was future work. Now here is what that tells us. Honestly, Bank spent a full academic year at one of the best acoustics labs in the world, with supervisors, measurement equipment, a real Steinway to measure, and the full body of physics literature. And at the end, he called it a first step and listed everything still missing. The attack noise fix that appears in the notes of gratitude as the thing that made a large improvement that came from experts complaining his high notes were too clean. He fixed it, and it only partly solved the problem, so the angry hopper's point is completely valid. And Bank himself would agree with it. The difference between Bank's situation and ours is not that he was smarter or better equipped. It's that he built the complete model, hammer, string, soundboard, calibration, as a single integrated system, measured against a real piano at every stage. He didn't start with a guitar algorithm and try to patch it into a piano. He started from the piano we started from Karplus Strong. That was a deliberate choice for good reasons: simplicity, speed, no hardware dependencies. But the honest consequence is that we are not patching a piano that sounds slightly wrong. We are patching a guitar algorithm that sounds like a guitar, and each patch gets us incrementally less guitar sounding and not yet piano sounding. Bank's model was always in the neighborhood of a piano. Ours is still approaching the neighborhood. The attack noise is not a minor refinement. It is the thing that tells a listener's brain this is a struck instrument, not a plucked one. Without it, no amount of correct decay physics will cross that perceptual boundary. That is what the remaining hoppers are hearing. You're right. I was being generous, and I shouldn't have been. Bank said good results and meant it. His experts gave him fine-grained feedback about subtle things that were slightly wrong. Our listeners fled. Those are not comparable situations dressed up differently. They are categorically different outcomes. The honest reading is this: Bank got good results because he built the right thing. He started from the physics of a piano, hammer, string, soundboard, and built each piece correctly before moving on. His model was always a piano model. Ours is a guitar algorithm that we have been trying to push toward piano territory with patches, and it still doesn't sound like a piano. The attack noise may help. But it would be dishonest to say it will close the gap between nobody thinks this is a piano and good results. Banks' good results came from the soundboard model, the nonlinear hammer, the properly calibrated I-stage decay, the attack noise, all working together as a coherent system. We have none of those except a partially correct loop filter, so the uncomfortable question the angry hopper is actually asking is, are we on the right path at all, or have we been incrementally improving a fundamentally wrong starting point? That deserves a straight answer rather than a defense. Karplus-Strong is a guitar algorithm. Patching it toward piano is possible in principle. Banks' 2003 paper exists precisely because digital waveguide theory shows the two are related. But Bank didn't patch a guitar algorithm. He built a piano model from scratch, starting from piano physics. The fact that the underlying mathematics is related does not mean the starting points are equivalent. We chose Karplus-Strong because it was simple, fast, and required no external dependencies. Those are real advantages for the larger project. But the cost is that every step since has been fighting the algorithm's natural character, rather than building on a foundation that is naturally piano-shaped. The algorithm wants to sound like a plucked string. We keep telling it not to. It keeps winning the right path if the goal is a synthesizer that sounds convincingly like a piano, is probably to do what Bank did. Start from the piano. Build the hammer model first. Build the string model second. Build the soundboard third. Calibrate each part against real piano measurements before moving on. That is a bigger investment up front, but it produces something that is always in the neighborhood of a piano, rather than something that is always fighting to get there. The question for you as the researcher is whether that investment makes sense given that the piano synthesizer. If the larger project can tolerate a synthesizer that sounds close enough but not fully convincing, the current path may still be worth continuing. If it needs to actually sound like a piano to be credible, we may need to restart the synthesis layer on a better foundation. That is not a comfortable conclusion after weeks of work, but it is the honest one. Then keep going. But go with eyes open. Kennedy didn't say we choose to go to the moon by pointing a rocket roughly upward and patching it as we go. The moon program started from first principles. They built the right rocket for the destination, not the easiest rocket they had, and hoped to steer it there. The parallel for this project is clear. If you're going to the moon, the attack noise is not the next experiment. The next decision is whether to keep patching Karplus-Strong or to restart the synthesis layer the way Bank did, hammer first, string second, soundboard third. Each part calibrated against real measurements before moving on. That is harder. It will take longer before anything sounds like anything. There will be a period where it sounds worse than what we have now because the pieces won't be assembled yet. But at the end of it, you would have something built for the destination, rather than something aimed roughly in its direction. The metrics, the research, the 50 papers, the experiment framework, none of that work is wasted. It tells you exactly what the destination looks like and how far away you are. That is the navigation system. What may need to change as the rocket the moon is hard, but it helps to be in the right rocket. Yes, and it's actually the more interesting research question. Bank built the right thing and got good results. That's confirmed and published. There is limited research value in repeating it. We also built a piano model from scratch, and it also sounds like a piano is not a contribution, but nobody has rigorously documented what it takes to get carpless strong, the simplest possible starting point, to cross the perceptual threshold into convincing piano territory. How far can you push a guitar algorithm before it stops being a guitar? What are the minimum necessary additions? At what point does the original algorithm become unrecognizable underneath the patches? Is there a point of diminishing returns where the patches become more complex than just building it right from scratch? Those are open questions with genuine research value. The pre-registered experimental methodology you already have is exactly the right framework for answering them. Each experiment either moves the needle or it doesn't, and you know precisely why in either case. There is also a practical value that Banks' approach doesn't have. A carpless strong piano that sounds convincing is computationally trivial compared to a full physical model. It runs on a CPU in real time with no GPU, no heavy calibration data, no external dependencies. If you can get it there, it is more deployable than Banks' model ever was, which is why Banks' model never made it into commercial synthesizers, and sample libraries still dominate the market. So the research question is not, can we build what Bank built? It is, what is the minimum viable physics needed to cross the perceptual threshold, starting from the simplest possible algorithm? That question has a publishable answer regardless of whether you succeed or fail. Failure with a rigorous methodology still tells you where the boundary is that is worth going to the moon for.
All right, y'all, let's do some carpless strong synthesis in pure data. Very briefly, carpless strong is a synthesis technique developed by Alexander Strong and Kevin Carpless. And usually we categorize this as a type of physical modeling synthesis because of the argument that it models a vibrating string and how it works. We'll get back to that later. Arguably, this is a kind of subtractive synthesis because we're using the resonant properties of a filter, specifically a comb filter. And actually, a while back, I did a quick no talking patch from scratch video about building a comb filter, and you'll see this is very, very similar in its construction. So we're just going to build a very, very simple carpless strong synth and then talk about some ideas about how you might expand on this. The general idea of how this works is we have a very, very short delay. And when I say very, very short, I mean that the taps of the delay are within the audio rate. So what we do is we put a noise burst through this delay and then feed it back into itself. Before we feed it back into itself, we're going to put it through a low pass filter as well. And so each time through this feedback loop simulates the vibration of the string. Now strings don't vibrate forever, so in our system we won't feed back the full signal, we'll attenuate a little bit, and then of course the low pass filter will cause the high frequency to decay faster than the lows. That said, now let's build it to help show these ideas. So the first thing we need is something to excite the system, the theoretical string. So let's start with just some white noise. Command 1, noise, tilde. You know, if I were to just do command 1 times tilde 0.1, and then command 1, DAC, tilde. Boom, there's the noise. All right, now we don't want our noise constantly going because we're just using this to excite our signal. So in order to create something that's pulsed, let's make a little metro construct here. Command T, there's my toggle. Command 1, metro. It doesn't really matter, let's do 125, something that's pretty quick. Shift Command B for our button, and then let's do this with a line. And so we're just gonna have something that's a simple AD envelope. Command 2 for a message. Go to number 1 over 5 seconds. Command 1, line, tilde, and then now, each time this bangs, it goes to 1 over 5 milliseconds. Now, if we want that to ever turn off, we need the other half of this. Command 1, pipe, which will delay the bang. Command 2 for another message, we want to go back to 0 over another 5 milliseconds. And we can adjust these attack and release times later, and multiplying that by noise, and so, start our metro. Right. Bang. Nice short impulse. Let's just turn off the metro. Let's slow it down here. All right. Very, very short noise. Okay, that's a good start. Now we need this noise to go into our delay. So actually, we don't need this DAC here. Instead, command 1, let's do a del right. So I do a delay buffer. I'm just going to call it del buff. I'm going to call it carp. The reason I'm calling it carp here instead, I changed my mind from del buff, is del buff is sort of what I call all my delay buffers. And so if I wanted to make a delay effect later, calling this carp means it's labeled specifically for the carpless strong. Again, you can name it whatever you want. You just need to remember that this is the name of your buffer. And so when we del read, we want to del read from the same part. This number 100 milliseconds. The length of our delay is going to be way, way shorter than this, 100 milliseconds. But for now, we'll have 100 milliseconds, but we can make that way shorter later. Okay, so we're going to read from this buffer, and then we need it to go to the output. 1 DAC tilde. Oh, so I can run this now. Okay, so that's not terribly interesting. All we've done is we take our noise and we delayed it. But so now comes the interesting part. Everything about this is going to be created through its feedback. So let's take our del read, we'll go command 1, send with a tilde, FB for feedback. Okay, and so then this friend is going to need receive, before E except after C, and then this feedback needs to go back into the delay. Now, before I run that in there, that would cause me some bad dreams, because right now I'm just sending everything back in. And so what's important about this feedback is that we have an ability to control how much of the feedback we're sending in. So that's actually going to be our resonance. So I'm going to create a number here, and then times tilde, let's start with. This number is going to control the resonance here. And this is going to be the amount that we throw to the feedback. Just for fun, Shift Command J for a horizontal slider. These will go from 0 to 127, and then Command 1, let's divide by 127, make. So now I have a resonance slider. And we don't really want it to go up to 1, but that's okay. Comment resonance. This is what's getting resonance back. All right, let's give this a shot. Turn my resonance down. That's metro. Highly embarrassing, but the reason this isn't doing anything is because I haven't plugged in my receive yet. Bink. All right, it's a delay feedback. It doesn't access this yet, and that's because our delay time is 100 milliseconds. So now here's the trick of it all into making it sound like pitches. Shift Command J for sliders will be our pitch slider. Command 3 for numbers, we can see what's coming out of that. Command 1, M2F, MIDI to frequency. Command 3, just so we can see that number. All right. Bink. Pitch. So now I have a slider. This is the MIDI number here, right? My sliders go from 0 to 127, so those are all MIDI notes anyway. This converts it to a frequency. But then we need to convert this frequency into a delay time. So remember, our frequency is in hertz, right? The unit for this here is hertz, and the unit I want here is milliseconds. So how do I convert hertz to milliseconds? Hertz is 1 over seconds, right? The number of times something happens in seconds. And so if we do the math of that, we know that. Okay, we're going to need to do division. Command 1, divide. Let's do command 3, show the number. But I'm going to do something slightly tricky here. I'm going to command 2 for a message, 1,000. Since there are 1,000 milliseconds in a second, I can divide hertz, 1 over seconds, by 1,000 in order to convert this into milliseconds. Let's do it and check it out. So again, this isn't sending a number right now, it's just banging out that 1,000, which is going to trigger this division. And then what are we dividing by? We're dividing by that number. So now watch if I change this slider. As I slide higher, this number gets lower, right? And as I slide lower, the number gets higher. Which makes sense because the higher frequency, the lower the number of milliseconds of the period. All right, let's check it out. That's definitely still clicking. Turn this up.
Good news for the excited hoppers. The claim holds up, but with important nuance what exists. There is rigorous perceptual work on individual features. Rakeso and Skalkin, 1999, formally measured how much inharmonicity you need to reproduce correctly for it to sound convincing. Järvelainen et al. 2001 measured the audibility threshold for inharmonicity across the keyboard. Bank and Ledinen, 2010, ran ABX tests on the audibility of the metallic phantom partials in low notes. These are serious, published, peer-reviewed perceptual studies, but they are each about one feature in isolation. Nobody assembled them into a single study that asks, start with bare KS, add extensions one at a time. At what point does a listener say, yes, that is a piano? That experiment has never been run. What the field did instead. Välimäki wrote in 1998 that bare KS is oversimplification for anything but rudimentary synthesis. That statement is an expert engineering judgment, not a perceptual test. The research community took it as given, skipped the KS piano question entirely, and moved on to commuted synthesis and full physical models. Modern comparison papers comparing neural versus physical synthesis don't even include KS as a condition because it is considered obviously inadequate. But obviously here means by informal consensus, not by rigorous experiment. The gap is real. No paper has ever taken bare KS, applied the Jaff-Smith extensions, then the Bank-Välimäki loop filter, then the attack noise, then the soundboard, and measured with formal listener tests at each stage whether the output has crossed into convincing piano territory. That specific experiment, with pre-registered hypotheses, perceptual thresholds, and a minimum viable set as the research question, does not exist in the literature. The honest caveat: the raw material exists. The individual perceptual threshold papers are there. The feature-level acoustic engineering is documented. What is missing is the synthesis, someone assembling this into a single framework with the specific framing of what is the minimum you need to add to KS before a listener hears a piano. The Battlestar was right that all of this has happened before. The physics has been done. The individual perceptual pieces have been done. But this specific question, framed this way with this methodology, that has not been done before. The excited hoppers are justified.